Keeper 3.2, the definition of the derivative. All right, so we've already looked at, in the last Keeper, we looked at the definition of a derivative at a point. And we also looked at the velocity formula, which was another alternative form of the definition of a derivative. This is actually what we're doing today, is the formal definition of a derivative. If you look, you can kind of see it's a combination of the two formulas that we worked with yesterday. So your formal definition is the limit as h approaches 0 of f of x plus h minus f of x all over h. All right, so let's kind of get an idea of what this formula is and kind of where it came from. So the example says label the following on the picture. Now, if we label the picture accurately, we should have a pretty good understanding of why the formula is what it is. So the first thing they say to label is f of x. So to label f of x, I basically identify where x is, and I put a little dot there, and I go across to the y-axis, see where it crosses, and wherever it crosses the y-axis, that's my f of x. Now, if I wanted to label f of x plus h, again, I'm going to do the same thing. I'm going to go to x plus h, draw a little line up, or see where it crosses my graph, and then I'm going to draw a line over and label that f of x plus h. Now, h itself, that's the next thing they're asking for. H is just the distance between x and x plus h. That distance, what we're adding on, is just h. So that distance right there is h. And then if I wanted to know f of x plus h minus f of x, that would be this distance. So the distance between f of x and f of x plus h would be simply f of x plus h minus f of x. All right, so now the important stuff. The first one says find a segment whose slope represents f of x plus h minus f of x all over h. In other words, find a segment who represents a change in y over the change in x. This h right here is my change in x. In other words, they just asked me to find the secant line. Well, again, thinking back, to your geometry days, your secant line, it was a line that crossed the circle at 2 points, almost like a chord. So my secant line, or my f of x plus h minus f of x over h, is just going to be a line that goes through these 2 points. So I have a change in y over the change in x. All right, the next one says the limit as h approaches 0 of f of x plus h minus f of x all over h. And again, that is my definition of a derivative, or my slope of the tangent line. So if I think about it, if this line that I just drew, this one right here, this secant line, if that is this formula over here, then to find the limit as h approaches 0, all I need to do is reduce h. So I need to shrink h all the way back down to 0, and when I do that, I'll be sitting right here at this point. So again, I'm going to reduce h to 0, and I get a line that touches my graph or bounces on my graph right here at this one point. And so the limit as h approaches 0, f of x plus h minus f of x over h is my tangent line at the point x. All right, for the next example, they're asking us to find the equation of the tangent line. They're giving us a function, it's a quadratic, and they're telling us at x equals 2. Now, because they told us at x equals 2, technically I can use the formula that we learned last Keeper with the a's in it. But because I'm trying to show you how the definition of a derivative works, I'm going to go ahead and use the definition of a derivative to find my answer. So I'm starting off with my formula, the limit as h approaches 0, f of x plus h minus f of x all over h. And I'm going to start with this first blue part where it says f of x plus h. Again, all that's telling me is that everywhere I see an x in my equation, I'm going to put x plus h. All right, once I do that, then I'm going to subtract f of x off. Well, f of x is the entire equation. So when I do that, I'm going to get negative 2, x plus h squared, plus 3, x plus h minus 4. That was this blue part. That was the f of x plus h, minus my f of x, well, minus my entire equation all over h. From there, it's just a matter, just like before, it's just a matter of simplifying over and over until you can clean this all the way up. So as I simplify my top, I'm going to multiply out the x plus h I'm distributing the 3, and I'm distributing this negative sign. And so I'm left with negative 2x squared minus 4xh minus 2h squared plus 3x plus 3h minus 4 plus 2x squared minus 3x plus 4. Now that seems like a whole lot, but if you did it properly, and this is kind of how you know whether you're on the right track or the wrong track, your stuff should start canceling out. There should be a whole bunch of stuff, at least like 3 things that cancels out in your problem, depending on what your original equation looked like. So when I do this, I notice I have a negative 2x squared and I have a positive 2x squared. That's going to cancel. I have a positive 3x and I have a negative 3x. That's going to cancel. And then I have a negative 4 and a positive 4. That's also going to cancel. So once I cancel out all that, I'm left with negative 4xh minus 2h squared plus 3h over h. From there, I can take out a h out of my numerator, or take out a h out of every single thing, divide everything by h, and I'm left with negative 4x minus 2h plus 3. All right, using our knowledge from the second unit, the limits unit, I know that all I need to do to find my answer is plug in my limit. So as h approaches 0, I'm plugging in 0 for h. And when I plug in 0 for h, I get negative 4x minus 2 times 0 plus 3, or negative 4x plus 3. Now, that is the derivative. That's the derivative of the function in general, right? If I want to know the derivative at a particular point, I'm going to take that point, or that number, that x value they gave us, in this case is x equals 2, and I'm going to plug it into my function for my x value. So again, to find the derivative at 2, I'm going to plug in my value at 2. So I have f of 2 is negative 4 times 2 plus 3, which is equal to negative 5. That's the slope of my tangent line at 2. Now to find the equation of the tangent line, I have my x value is 2, but I also have to find my y value. So to find my y value, I have f of 2. I'm just going to plug 2 into my original equation. So negative 2 times 2 squared plus 3 times 2 minus 4 equals negative 6. That is my y value. And then I'm going to use my point slope form to get my final answer. And I'd have y plus 6 equals negative 5. That was the slope, x minus 2. This next example, we're doing the very same thing. They're not asking us to find the equation this time. They just want the derivative. So I can just use my formula. They didn't give me a point, so I have no option but to use that formula to find my answer. So again, I'm starting off with my formula, and I'm going to start by plugging in the x plus h. So my first part would be 3 over x plus h minus 2, and then minus f of x, which would be 3 over x minus 2 all over h. From there, I'm going to get a common denominator. So I'm going to take this x minus 2, and I'm going to multiply it times the 3. And then I'm going to take this x plus h minus 2 and multiply it times that 3. And that will give me my common denominator. And so I get 3x minus 2 over my common denominator minus 3x plus h minus 2 over my common denominator all over h. Now that I have a common denominator in my numerator, I can mush it together, and I get 3x minus 2 minus 3x plus h minus 2 all over that common denominator, all over, still over h. Now again, just simplifying my equation, if I simplify my numerator, I get 3x minus 6, I distribute it, and then distributing a negative 3, I get negative 3x minus 3h plus 6 over that common denominator, and then I simply did a keep change flip to change my division to multiplication and made it times 1 over h. All right, so I'm going to continue to simplify that numerator, and I get stuff canceling out, so I get 3x, negative 3x cancels, and then I get the negative 6 and the 6 that cancels, and so on top I'm simply left with negative 3h over that common denominator again times my 1 over h. All right, so then I can simply take out these h's, cancel them out. So this h and this h get canceled out. I'm left with negative 3 on top over my common denominator. The second I cancel out that h, I know I can go ahead and find my limit. I find my limit by plugging in 0 into my h's. So I get negative 3 over x plus 0 minus 2 times x minus 2. Simplify that, I get negative 3 over x minus 2, and then I want to kind of make it look cute, so I don't want to write that repeated factor twice. I'm just going to do x minus 2 squared in my denominator. All right, so my final answer, my derivative equals, or f prime of x equals, negative 3 over x minus 2 squared. All right, next we're going to look at derivatives from a chart. It says the traffic speed S along a certain road in miles per hour varies as a function of traffic density Q, or the number of cars per mile on a road. Use the chart to answer the following questions. All right, so this first question, they said S of 100. Notice they did not say S prime. They're just asking for S of 100. That's simple function notation. They're not asking for anything fancy. So I'm just going to find 100 on my chart, and I'm going to find the S value that corresponds to it. So I'm looking at my chart. I have 100 for Q. My S value is 45. All right, the second one says S of 120. So I find 120 on my chart. And then I locate my S value, which is 39.5. All right, and again, that's miles per hour. All right, the next question says find the average rate of change from Q equals 110 to Q equals 120. Remember, average rate of change is your slope of your secant line, or your old school slope, your y2 minus y1 over x2 minus x1. We're going from 110 to 120, and these are the y values that correspond to it, 42 and 39.5. So our x1 is 110, x2 is 120, y1 is 42, and y2 is 39.5. Again, I'm using my old school formula just to make my life a little bit easier. So I have y2 minus y1 over x2 minus x1. I'm plugging in those values, so I get 39.5 minus 42 over 120 minus 10. Simplifying my numerator and my denominator. On my numerator, I get negative 2.5. My denominator, I get 10. Dividing that out, I'm left with negative 0.25. And again, that would be miles per hour per mile, or per car per mile. All right, so again, that's we have to use units, and it's change of y over change of x. All right. Okay, this next example asks us to estimate the instantaneous rate of change at Q equals 130. Now, the problem with this is that I can't actually find the instantaneous rate of change. I can't find the derivative because I can't calculate the limit at 130, because the chart only gives us from 120 to 130 and 130 to 140. They don't give us any like in between values, so I can't actually find the derivative. All I can do to estimate it. Now, what I'm going to do to estimate it is I'm simply going to find the average rate of change before 30. So I'm going to do like the average rate of change from 120 to 130, and then I'm going to do the average rate of change from 130 to 140. And then I'm going to take those two numbers, whatever I find them to be, and I'm going to find the average of that to estimate my instantaneous rate of change. So to start, I'm going to do my average rate of change from 130 to 140. So I have 35 minus 37 over 140 minus 130. I simplify that to negative 2 over 10, and then I go ahead and work that out to be negative 0.2. Now I'm going to find the average rate of change from 120 to 130. So I have 37 minus 39.5 over 130 minus 120. Simplify that to be negative 2.5 over 10, which is negative 0.25. So again, once I have those two values, so I have a little bit of what's going on before 130, I have a little bit of going on what's after 130. I'm going to take the average of those two numbers to estimate my instantaneous rate of change. So I'm going to take the average, or find the average of the slope of the secant line from 130 to 140, and then the slope of the secant line from 120 to 130. Now, if you remember, for averages, all you do is you add up your numbers and divide by however many numbers you had. So I'm going to add up my two numbers, negative 0.2 and negative 0.25, and I'm going to divide that by 2, and I get that slope of my tangent approximately equals negative 0.225. Now, again, remember, that's not an exact answer. That's just approximately what's going on based off of what was happening before and after 130. Now they want us to estimate the instantaneous rate of change at 140. So in the last problem, we had a problem because we didn't know what was going on before 130 and after 130. But in this problem, I have an issue because I don't have any information after 140. So I can't use the same method. So the only thing I could do to estimate this is actually just find the average rate of change before 140. So I'm going to use 130 and 140. Even though they're asking for instantaneous rate of change, I'm going to go ahead and find the average rate of change because that's all I can do. So I can hope that the average rate of change is somewhat close to the instantaneous. There's a chance that it's extremely far off, but I have no other choice in how I can calculate my estimation. So to find my slope of my tangent line, I'm going to actually just find the slope of the secant line from 130 to 140. So I have 35 minus 37 over 140 minus 130. Reduce that to -2/10 or -0.2. All right, so now we're going to look at what makes a graph differentiable. In order for a graph to be differentiable, number one, it has to be continuous. Now, we talked about in Unit 2, we talked about something being discontinuous, meaning, or continuous, meaning that it didn't have any removable discontinuities, it didn't have any infinite discontinuities, and it didn't have any jumps. All right, so it doesn't have any holes, it doesn't have any asymptotes, and it doesn't have any jumps. Now we're going to add on for differentiability. It also cannot have any cusp, any corners, or any vertical tangents. So let me try to draw that out real quick. A cusp would be something like that. A corner would be something like that. And a vertical tangent would be something like that, where it goes straight vertically in the middle somewhere. All right, so if you have any of these three, plus if you have any of the discontinuities that we already learned about, your graph is not differentiable at that point. All right, so this example says find the x values where f is not differentiable and state the reasons. So I just going to look at my graph and I'll move left to right. The first place that I see is right here at -1. It seems to go straight here. And so that looks like a vertical tangent to me. So at x equals -1, I said vertical tangent. Then I want to look over here at x equals 1. I notice I have a break in my graph. So that looks like a jump. So at x equals 1, I have a jump discontinuity. And right here, I have a sharp turn, like an absolute value graph, which again makes me uncomfortable for differentiability. So I'm going to say at x equals 3, I have a corner.